Hey guys, I think we're going to need a bigger boat. All right, but seriously, today we're going to be talking about great white sharks. I'm just picturing what I'm going to do to edit this video. All right, anyway, today we're going to be talking about the lynx of great white sharks. So researchers who wanted to gain some insight about the average lynx and the distribution of the lynx of great white sharks captured 44 great white sharks and recorded their lynx along with other things, and of course tagged them for their research purposes. All right, whew, I feel a lot better now. I don't know about you, but I think I'll get back in the water for a while after seeing that photo. All right, so here are the links of 44 great white sharks. Enter the data into your graphing calculator and write the 5-number summary, IQR, mean, standard deviation, and yeah, good stuff. All right, so to save you time, I actually put it in the calculator for you because 44 doesn't seem like a lot, but man, it's really tedious, and you're welcome. So anyway, all I did is I went to stat and I went to edit. This is our data we used yesterday, so I went ahead and just put it in list 2 just in case I wanted to go back if you guys had questions on this data, and I don't have to put it all back in there again. Anyway, if we go all the way to the bottom, it'll see you have list 2 44, which tells us that there are 44 put in the list. You might skim over the data real quick to see if you have any clear outliers or mistakes or something, typos, but I tried to be careful whenever I did it. So good to go. We want to find the one variable stat, so I'm going to click stats, arrow over to calculate one variable statistics. It is list 2 because that's where I put it, and then hit calculate. The X bar is our mean, so that's the average shark length, which would be 15.64 feet. That's a big shark. The sigma of X, that's going to be the sum of all the X's, so that's the sum of all the shark lengths together. So if we put them all head to or nose to tail, I don't know how you describe that, that's how long they would be. The sum of the X squared, it's going to be some of the deviations. And then if we divided that number by our n minus 1, which would be 43, that would give us a total variation. The sigma, or the S sub X, is the standard deviation for our sample, and it's not all the sharks in the ocean, so it is a sample, so we divided it by n minus 1 instead of just n, which would give us a sigma of X if it was the population. The sigma of X, the standard deviation for a population, will always be slightly smaller, but as our sample size increases, the difference between those two is minimized because numbers. Then if we arrow down, that will give us our 5-number summary, minimum, maximum, and the quartile. So I went ahead and move those over there so you can read them a little bit better. All right, so you can fill in those that information, our summary stats. Next question, part B, wants to know what is the interquartile range. So we're going to take our Q3 of 17.5 minus our Q1. When we do that, we get 3.95, so that's the interquartile range. The left fence, we take 1.5 times the interquartile range, which will give us this new value, and then we subtract that from the first quartile to get our left fence and add it to our third quartile to get our right fence. Visually, what's going on, there's our interquartile range, which is the width of the box, right? And then we do 1.5 of that value. We subtract it from list 1, okay? So it looks like we don't have any outliers on the left side. Our minimum value of 9.4 is within the left fence, and so it's not considered an outlier. And then our right fence, we add it to our third quartile, and it looks like our maximum value of 22.8 is within the right fence as well. So do we have any outliers? No, because our maximum and our minimum are within our left and our right fence, or you can just say within the fences. All right, so visually that's kind of what's going on. Graph that box plot, which is cool. Are there any outliers? We said no, because they're within the fences. Next thing we want to do is we want to visualize the data to make sure that it's unimodal and symmetric so that we can see if we can use a bell curve. So to do that, I'm going to go second, y equals a stat plot. Make sure you just have one of them turned on. I'm going to go to the histogram, plotting list 2, because that's where we put our data. And then I'm going to hit zoom 9, which is going to zoom stat. So that's our histogram there. Now, if we want to fill it in, like if I hit trace, excuse me, it's going to have a weird window. If you see the min and the max right there, that's a really weird window. We want to fix that so that it matches up with the one that I gave you. Excuse me. Which is going from 8 to 24 with a bin size of 2. So go to your window button. Of course, you guys don't have to do all this because it's a lot of data to put in there. For the minimum, I'm going to do 8. The maximum, I'm going to do 24. Bin size of 2 for the X scale. And then I'm going to hit graph. And now it should match up. Oops, sorry, just graph. should match up here. So from 8 to 10, that bin only had 1, which was the smallest one, that 9.4 that we had. And then we had 13, 9, 13, 7, empty, and then 1. And again, these are not considered gaps because there's not multiple bins that are empty between two groups of data. There's just, we didn't have any sharks that were anywhere from 20 to 22 feet long, and we didn't have any sharks that were anywhere from 10 to 12 feet long, which you can see over here. If we increased our sample size to 100, chances are we would have found a shark that was that long. Dang, that's a really long shark. Is it 20? Yeah, 22.8. Ooh, that's really frightening. Anyway, it makes me not want to go back into the water. I just want to show you something. If we slightly, so this looks more or less unimodal and symmetric. Again, you might say, okay, there's two modes, so you could say that it's bimodal. But in general, it tends to be, it would be close enough for us to be able to fit that with a normal model, no problem, based on our data. The other thing is, look what happens when I adjust not even adjusting, well, I'm adjusting the window, but instead I'm starting at 9, and I'm going to go up to, I think 25. Yeah, 9 to 25 with an X scale of 2. And then when I hit graph, look how different that graph is to that one. Like, that is incredible. I wonder if I lock this here. Oh no. Well, so I got shortcut keys. Yeah, there we go. You see, those are actually, it's the same data. I should really change the color of one of them. But it looks much more clearly unimodal instead of bimodal, and all we did is we shifted the bins left or to the right, going from 9 to 25 instead of 8 to 24. It's incredible how much the histogram can change just by changing the window. And again, that's the exact same data. Another thing, if we wanted to have maybe, and this clearly looks very unimodal symmetric. I don't see any tails, doesn't look necessarily skewed or anything. So we could definitely use a bell curve on this one. But also, if I would have changed it to the window and instead changed my X scale to 1, that would make it, more precise. And then if I hit graph, you can see the histogram form here, which again looks roughly unimodal and symmetric. So it's good enough for us to be able to use a bell curve, even though you might say, okay, you see two clear modes there. But keep in mind, what it's a sample from all the sharks, and if we filled in all the sharks, we'd probably have more that would fill this in, and it would probably, as we sampled more and more, it would become more nearly normal, which is interesting. So we believe that the population itself is probably normally distributed, and it is. Okay, so the next thing is we want to look at our bell curve or the Gaussian curve or normal curve. Again, they have 3 different names, and that is this model here. How well does our distribution, which is the green histogram here, and again, the histogram could have looked different if we just even changed it slightly. It's kind of crazy. How well does the model fit? Is it unimodal? Is it symmetric? Does it look like it's appropriate for us to use the model to summarize the distribution? So if we do, the model we would use would be parameterized by the mean, which is the average shark length, which was about 15.6 with a standard deviation of 2.56. That information came right here. 2.56 was the standard deviation, and the mean was the 15.6. So anyway, that's how we would parameterize the bell curve that would the model that would represent the distribution of what we believe all the sharks, great white sharks, are from that region. And of course, bell bottoms, fun stuff. All right, bell curve, Taco Bell, T-Bell. Sounds really good right now, but that's because I'm recording this at 1 o'clock in the morning, and T-Bell always sounds good at 1 o'clock in the morning. Okay, so here we have, basically we can only use bell curves with unimodal and symmetric data. If it's skewed to the left or skewed to the right, we can't, because the mean would be skewed towards the tail. But in this case, we don't have to worry about that. We don't have any outliers that are going to increase our standard deviation and throw off our model. Also, we don't have any gaps between the data, like yeah, I had to make that gap because there's not really naturally a gap there. I've been hiding that from you the whole time, and now you just found out. I'm not a liar. I have a problem. Anyway, so there is a gap between the two data. In that case, that would not be appropriate to fit with a bell curve, neither would this one, unless we got rid of the outlier, if we could justify doing that. All right, normal models is really a family of models. There's a normal model to fit any possible distribution as long as it's unimodal and symmetric, parameterized by the mu and the sigma, Greek letters for parameters. We use Latin letters for statistics that come from the actual data itself. When we're talking about like theory or a model, like in this case, we use Greek letters because Greek comes before Latin. At least like the Hellenistic era came before the Roman Empire or whatnot. Anyway, so we have the mu, which is the mean, and the standard deviation is the width from the center of the bell curve to the inflection point. Again, that's going to be there. You can have really skinny and narrow ones. You can have shorter and wider ones, but in general, we just show them that look like this aesthetically pleasing version, and we just change the X scale in order to make it stretched out or skinnier. Okay. All right, so part C, calculate the percent of observations that fall within 1, 2, and 3 standard deviations of the mean. How well does this compare with the empirical rule? So let me show you the empirical rule real quick. So it's called the empirical rule or the 68, 95, 99.7 rule. And what it says is within 1, 2, and 3 standard deviations from the mean. So 1 standard deviation from the mean is this red area here underneath the curve, okay? That it says that if a normal model, the model itself, not the data, but the normal model, 68% of all the data will fall within 1 standard deviation of the mean. Okay, 95% of the data from the model will fall within 2 standard deviations of the mean. That's the 95%, and then the 99.7 means when you go out 3 standard deviations. So we're just increasing our width here. Now that we go 3 standard deviations, 99.7% of all data should fall within 3 standard deviations. Now again, the empirical rule is true for the model, but not necessarily for the distribution, because distributions, models are just quick, useful estimates or representatives of the actual data itself. Okay, so you got to keep that in mind. So I like to call it the empirical rule because I like to ask you what these numbers are on the test, and if I tell you it's this rule, you already know the numbers. So anyway, it goes by either one of those two names. Another thing is, so this model, let me go ahead and show you that part real quick. So this model, I'll show you on this one because it's the same thing. So it's centered at 15.6 with a standard deviation of 2.56. There should be a space right there. There we go, much better. So we go over 1 standard deviation. So we add a standard deviation of 2.56, add another standard deviation 2.56, and another one. Okay, and then you subtract 2.56 3 times to get these values here. Okay, so these are going to be our left and our right kind of barriers or endpoints of our interval for 1 standard deviation, 2 standard deviations, and 3 standard deviations. And what we're going to do now is we're going to see how well did our actual data, our model, fit, how well did our actual data fit into this model, how accurate were those percentages. So this is actually kind of fun. So we're going to do 1 standard deviation. So our lower and our upper limit for 1 standard deviation is 13.04 and 16.16. So you can take those values and you can just copy and paste them. I'm just kidding. I can copy and paste them, but you can't. I don't know. So I can put that. Will it work for the lower? Hey, that's so cool. And this one for the upper. All right. And then the question we have now is, what is the number of shark links that we had that were strictly between those two? So what I'm going to do is I'm going to sort the list. So sort ascending. And I'm going to do this for list 2. So second 2. And then I'm going to go in and edit and look at the data itself. So I'm going to count how many were between 13.04, which would be this one, would be the starting one, all the way up to 18.6. We have 1, 2, 3. Okay, so that was 32. Hey, there's a faster way of doing that. So this was 31, and that would be 30. Okay, so the number that we had was 30. Wow, wasn't that like so exciting? Isn't playing with data fun? All right, so we had 30. What percent of all 44 sharks is 30? So I'm just going to quit out of this, and I'm going to do 30 divided by 44, which is going to be 68%. Oh, no way. That is really cool because our rule for the empirical rule was 68%. So we were supposed to have 68% of the data that fell within 1 standard deviation, right? And we did. Like, that never happens. Okay, models are not perfect. They're just quick, good estimates as long as they fit, like, well enough. I don't want to say good enough. That just sounded wrong. But anyway, okay, so let's do another one here. So now we're going to go 2 standard deviations. And I realize I'm going to have to do all this with you because I'm not expecting you to put that data in there because that would really suck. All right, so we want to know the number that are within 18. This one should be a lot easier because we'll just count the number of the ones that are not, and we'll subtract it from 44. Okay, so how many of them are below the 10.48? There's only one low one that wouldn't fit, and then 20.7. There's only, okay, so there's only two data that are outside 2 standard deviations. So that would be, our number in this case would be 42 that are within it. And then the percent, I gotta divide that out. So I'm gonna do second quit to go back to the home screen. Yeah, so 42 divided by 44, which is gonna be 90. No way. It's almost like this data was made up, but I promise this is real data from Australia, land down under. All right, and in our normal model, the empirical rule tells us that it should be 95%, and sure enough, it was like right on 95. So what about 3 standard deviations? So our limits are here. Duplicate those. Okay, so how many do we have within those values? I think that might be all of them. It is all of them. Is that edit? Yeah, because 9.4 is within that bound, and it's, yeah, so that's all of them. So that's easy. So our number in this case would be 44, which is 100%, and it was only supposed to be 99.7, which is essentially 100%. So wow, that was so stinking cool. We will do this again with other distributions because it's really fun to analyze how well our model actually fit the data that we had at hand. And yeah, so we'll do that again, and we'll see what happens specifically with when we try to fit a normal model with skewed data or bimodal data, and we'll see how it breaks down the whole system. So more fun stuff like that coming. Hopefully they won't be 44 sets of, a data set of 44, because it's just too much for me to expect for you guys to put in there. So yeah, good stuff. Moving on. Empirical rule, we already went over that. So it tells us 68% are within 1 standard deviation, 95 within 2, and 99.7. That's true for the model, but not necessarily true, for the distribution itself. In this case, it was true, which is fascinating. That never happens. All right, placement exams, number 12. An incoming freshman took her college placement exams in French and math. In French, she scored an 82, and math an 86. The overall results of the French exam had a mean of 72 with standard deviation of 8. So I am using a normal model for that, centered at 72 with a standard deviation of 8. So 72 plus 8, that's the width here to the inflection point, is 80, then 88, 96, right? Then subtract 8, subtract 8, subtract 8, okay? So when you draw a normal bell curve, which you don't have to on this, by the way, you just have to calculate z-scores. I just like to graph it out so you can visually see what's going on. Make sure you label it using our annotation here, like our coordinates, but our parameters for the bell curve, or for the model, which tells us it's a normal model of 72, 8, which is centered at a mean of 72 with a standard deviation of 8. And then for math, it tells us the mean score for math for everyone was 68 with standard deviation of 12. So 68 plus 12 would be 80, 92, 104. All right, this 104, obviously this is a model. Can you score higher than 100 on a test? Not on my test. So this tells us, it would be highly unusual to have somebody score above 100, and it's actually impossible. So again, keep in mind, this is just a model, and sometimes models, they kind of have their flaws, and this kind of shows, hey, that's a flaw, because that's not really even possible. Probably not. And then going down, 3 standard deviation would be 32 over here on the low end. Okay, so her scores, she had a score of 82 on the French exam and an 86 on the math exam. Which one of those scores was most impressive compared to their respective distributions of how the rest of the class did on the French exam and the math exam? So these are 2 separate distributions with 2 separate bell curves, essentially. And so what we need to do is find out, where does 82 fall? So if I look over here, apparently I didn't lock that one in place, which means this one's not locked either because I copied it. And not what I was trying to do. All right, so where does 82 fall? So that falls somewhere around here, and 86 falls somewhere around here. So both of these are going to be somewhere between 1 and 2 standard deviations above the mean, which would mean that would be our z-score. So let's calculate the exact z-score. So the observation, z-score is the observation minus the mean divided by our standard deviation. And this is what allows us to compare apples to oranges, or French score to math score. You can actually use this, it's kind of cool, to compare like male athletes to female athletes, right? So like Vanessa Williams or Serena Williams, I think Vanessa Williams is like more dominant, but if you're looking at Vanessa Williams, many people would say she's just a dominant athlete, and I would agree, she's totally a dominant athlete. But there's also like male athletes that are pretty dominant as well. So the question we might have, okay, so like Roger Federer or whatever. So if we compared Roger Federer to Serena Williams, or Vanessa, I get them backwards. Vanessa Williams. I think she's the better one. I don't know, the older one. Anyway, if we compare them, if they played a match against each other, she's going to get her butt kicked because men serve a lot faster, have faster, like fast twitch muscles and stuff like that. So it's just not fair, right? That's why we don't compete them against each other. But if you wanted to ask the question, how dominant is Serena compared to female athletes as Roger Federer is compared to male athletes? So if we looked at their Z scores in particular, we could actually be able to compare apples to oranges that we couldn't naturally compare either way. And we could see if she is a more dominant athlete or more impressive athlete compared to how far above she is compared to the other women tennis players, when we compare the same thing with Roger Federer against other male athletes, which is really cool because it kind of solves some issues that we might have when we're trying to score those things, if we hypothetically wanted to know that. And now I do, but I don't even care about tennis, but it's cool because math. Fun stuff. Okay, so comparing French to math tests, 2 different tests with 2 different means and 2 different standard deviations. Looking at the standard deviation for math, it had a lower mean, so people did worse in general than in math. Also, it had a larger spread, so there was much more variation in the test scores, where the French test had much more consistency in the test scores, and you can see that play out in the models themselves. Okay, calculating Z-scores. Observation, total aside, minus the mean divided by standard deviation, but hopefully you guys find that stuff interesting because I do. Anyway, so we subtract that as 10 divided by 8 is going to be 1.25. So she's 1.25, 1.25 standard deviations above the average score for French class, okay? And we can actually find the percentiles for that. Well, I think we do that tomorrow. So we'll find what her percentile rank is using the model and using the normal CDF distribution, which is kind of nice. But we'll do that tomorrow. All right, then for math, she was 86 minus 68, which is going to be 18 divided by 12, which is 1.5. So she was 1.5 standard deviations above the mean for the math score. So which one was more impressive? Which one was a more unusual score? Her French score or her math score? And it's not just her math score because 86 is better than 82. That's not how this works, right? Because we're comparing apples to oranges. It was a different test, right? And we can tell how impressive her score was based on how well she did in ranking of everyone else's, which would take into consideration distribution, like the mean and standard deviation. So overall, which one was more impressive? Her math score was more impressive because it had a Z-score of 1.5 instead of 1.25. So 1.25 would put us about here, 1.5 would put us about here, and yeah, that's pretty much it. And the Z-scores is just simply a units of how many standard deviations above or below the mean. If it was a negative Z-score, it would be below. And that's it. Okay, so let me show you another one, 20 or 16 MP3 players. So you even know what MP3 players are? Yeah, so 2 companies market new batteries targeted towards owners of personal music players. Okay, wow. Duratunes claims a mean battery life of 11 hours, while Rock Ready advertises 12 hours. Explain why you would also like to know the standard deviation of the battery lifespans before deciding which brand to buy. So the problem is that if one of them had a much larger spread, that also means that it's more likely that you would get like a lemon or a bad set of batteries that wouldn't last very long. So consistency is also important when you're buying something, right? So yes, if you have more spread, it also means you could get batteries that last way longer, which is nice. But with more risk, there's more reward as well. So it's kind of the question we're asking. Not only where are they centered at, but also what is the spread or the standard deviation for those, or the consistency or variation. Lots of different words for the same basic concepts. All right, so if Rock Ready had a larger standard deviation, not only do they have a larger mean average battery life, but also more variation or larger standard deviation, the batteries will be less consistent. You may get batteries that don't last as long. So if it's something that's really important, like, I don't know, you're taking these batteries on a backpacking trip where you're 8 hours away from, ask me how I know, 8 hours away from civilization, you might actually go with a brand that has a lower mean, but they actually have more consistency, because you don't want the risk of getting a bad set of batteries that die on you or something. But let's be honest, at that point we're using solar charging and stuff like that when we're out backpacking, like I did. Okay, so next question is, suppose you're headed for 8 hours at the beach. Which Supposed standard deviations for are 2 hours for Duratunes and 1.5 hours for Rock Ready. You're headed for 8 hours at the beach. Which battery is most likely to last 8 hours? So to calculate that within their respective distributions, we have to look at their z-scores. And just in general, all day today, you're calculating z-scores for the rest of the week, pretty much, and next week. So for Duratunes, centered at 11 with a standard deviation of 2, and then Rock Ready centered at 12 with a standard deviation of 1.5. Okay. Yeah, that's right. For some reason, I would think they would switch those, but that's it, I'm guessing. Okay, yeah, that's right. Okay, so centered at 11 with standard deviation of 2. So every standard deviation we go over is going to be 2. So 13, 15, 17. You should know how to label those, then subtract 2, subtract 2, subtract 2. Okay, let me show you a trick on that one, because sometimes those numbers are not just so easy to calculate. So let's start at 12 here, and then we're going to add to it 1.5. So we can hit plus 1.5, hit enter, and then hit plus 1.5 again, and then it's going to add 1.5 to the previous answer, and then just hit enter again, and it'll do it again for you. So that's an easy shortcut way to figure out what those links are. If we need to do another one, we can do 18. Okay, so that's going to give you these values that we got down here. If we want to do the same thing but going in the other direction, like subtracting 1.5 minus 1.5, and do the same thing, and it'll go right back to your mean of 12, and then you can go back the other direction. So that would give us 10.5, and then 9, and then 7.5. So even though I know you can probably do those in your head, this is a nice little trick that I use all the time in order to be able to fill in those things. Also, you see here that these are z-scores, so mean of 0, -1, 2, 3. Those typically we won't write those every time, but you can see them now. And on this one, you don't need to draw you don't need to draw the bell curves either. You can just kind of just calculate the z-scores. So anyway, Duratunes, if we go down to 8, 8's going to be right there, which is, oh, nope, it's exactly halfway between that. I knew that. So it's going to be a z-score of -1.5, meaning if it lasted 8 hours, or if it died at 8 hours, there'll be 1.5 standard deviation below the mean from what we would expect, which would be centered at 11 for the distribution for Duratunes based on whatever information they gave us. Same thing for this one. If we go down 8, that's actually be more than 2 standard deviations. In fact, like 2.6 repeating, so a little bit past halfway. All right, 2.6 repeating. So for which company's batteries would it be more unusual for it to last only 8 hours? So to die at 8 hours, it would be very unusual for Rock Ready, but a little more common for Duratunes because there's more area under the curve here. So you're more likely to have batteries that last at least 8 hours if you bought Rock Ready, which had a higher mean and a smaller standard deviation. So of course that should make sense, right? Had a higher mean and the batteries were more consistent. Duratunes, on the other hand, had a lower mean and less consistent batteries, which means you could have higher values, like 3 standard deviations above was 17, 3 standard deviations over here was only 16.5. But still, if you're worried about 8, this would be the ones that you would want, which would be Rock Ready. All right, that's it. So under 30 minutes, good to go. I hope you guys enjoyed that. I hope you guys have a good weekend. Happy Friday. If you haven't taken the quiz for me by now, you probably haven't watched this video by now either, so I don't know why I'm even like giving announcements through the videos if you guys are that far behind. Hey, that's something I need to think about. I should put more announcements and just in general. But anyway, make sure you get caught up. We are going to, remember our deadline is going to be in 2 weeks, so September 30th is when we're planning on taking the test over all of Unit 1. So that's going to be the deadline for all of your homework. So make sure you guys are staying caught up. If you have any questions, please join us for the office hours from 1 o'clock to 2 o'clock every school day. And I would love to help you guys and to see you then. So that's it. Have a good day and good weekend.